All right, hi everyone. Let's start. So let me repeat a little bit. Do a small recap. The question we're trying to answer is, suppose fn functions go to f. When do we have? When can we say that the limit and the integral can be swapped? Right, so that's the question. Okay, and then last time we said that a very so last time we showed that if you have uniform, that uniform allows you to swap. So uniform and continuous or bounded, like we talked about with Trevor. So if you have continuous or bounded, allows you to swap limit and integral. But again, when the set is compact. So let me mention that too. For compact set K. Right? Yeah. So, I mean, we're ahead of schedule, so feel free to ask questions. We can go as slow as possible. We have plenty of time. We're very ahead of schedule. Okay, so let me give a variant of what is called the monotone convergence theorem. For our level in the course. In the textbook is called the Leibniz theorem. So yeah, if you have, so that's the theorem. If Fn, F are from 0, 1 to R, satisfy the following. They're continuous, and they're increasing. So Fn is less than Fn plus 1, which is less than Fn plus 2 for all x. And finally, you have pointwise convergence, meaning for each x, they converge to F. Then you can lift it to uniform. Then we have uniform. And so corollary limit of the integral of Fn is equal to the integral of F. This goes by the name monotone convergence theorem. So here we have a sort of weak version because we had to add continuity and we had to add compact domain. So you can replace everything by a compact domain. There's nothing special about 0, 1. And continuous, like we talked with Trevor, you can replace this by bounded. Any questions, comments? Okay. Yeah, we're ahead of schedule, so please feel free. We can go very slow. You don't have to run. Okay, let's start the proof. Okay. Yeah, so we will do this by way of contradiction. Suppose there is some epsilon naught such that let me say the limit of the supremum of these guys supremum over x in 0, 1 of f of x, fn of x is bigger than epsilon naught. So meaning i.e. it does not go to 0. So that's our assumption that we will contradict. Okay, because we want this to go to 0. Right, right. Okay, so what's the idea? Okay, so first step, f. So let gn of x equal f of x minus fn of x. And it's positive because they're increasing to f. So let this. So this guy is. Yeah, so let this be that. It is continuous. So by extreme value theorem, the supremum of these guys is attained on some xn in 0, 1. Okay, attained. Okay. Oh yeah, I just want to confirm that that means uniformly continuous, or just no. I think you're confusing it. By double arrow, we mean uniform convergence. So when we write this, we mean exactly what we wrote here. So limit of the subnorm goes to 0. That's the definition of the double arrow. Yeah. Thank you. Yeah, please. We're very ahead of schedule, so you can ask as many questions as you like. Feel free. Like I'm doing extra things just so that we have things to talk about. So please feel free to ask questions. Okay, so it is attained somewhere, and so by let me call this star, which is our contradicting assumption. Therefore, thus the limit of this, g and xn is bigger than epsilon naught. That's very nice. We're going to use this. Let's call it double star. This is an improvement on our contradictory assumption. Okay. But 0, 1 is compact, so we're not using anything else. But 0, 1 is compact, and that implies that there exists a converging subsequence. I'm talking about xn. So there's just a converging subsequence xnk going to x0. So that's very, very useful. So compactness is essential in this proof. Okay. May I look at the, yeah, sure. So again, before we look at this, let's look at what the theorem says. The theorem says if you have these assumptions, then we have uniform convergence, right? And so we're saying that we don't have uniform convergence. Suppose that there is some epsilon naught that you don't have uniform. Not uniform. Okay, good. Yeah, feel free, guys. Keep asking your questions. I want to slow down as much as possible. Okay, so we have this compact. Now, let's study what happens let's study what happens at this point x0. This is a very special point, and we'll try to get a contradiction. Okay. So what do I want to say? Yeah, I claim. I want to claim that G. Okay, yeah. I claim that there exists an n such that for all n bigger than this capital N, we have that Gn of x is less than epsilon naught over 2 for all x in a neighborhood of x naught. So before I prove this claim, let me say why this finishes the question. Okay. Yeah. So right. So we fix delta. Yeah. So let me say why contradiction follows. Take nk large enough so that x and k is within, call this a delta ball, so that x and k is within this delta ball. Okay. Okay. Is that okay? So yeah, we say that. But x and k have the following property. G and k, x and k, is bigger than epsilon naught. This is double star. So that's one, that's two, and together we get a contradiction. So let's call this triple star. But for all x in B delta x naught, we have the opposite. So altogether we get, epsilon naught is less than this guy, which is less than this. And so we get the usual contradiction, 1/2. So that's how we get the contradiction. I want to try to draw some picture. So this is x naught, and this is the delta ball. And we found, this is a subsequence, so they converge to it. So no matter how small the ball, we can always find points from the subsequence inside. So that's what the subsequence is. But then we said that inside this ball, if this is epsilon/2, the graph of G falls below that. It falls below that in that, so it could be outside, but in this neighborhood is below epsilon/2. Okay. So now we're going to prove the claim that we can find some neighborhood where Gn of x is less than epsilon/2. Okay. Proof of claim. All right. Yes. So, what was the approach? Yes. So, fix epsilon. Let me put it over 4, and then we'll change it later because I don't remember exactly. So yeah, put epsilon over 4. By pointwise convergence, Fn going to F, there exists at x naught. We're doing it at x naught. There exists n epsilon large enough so that for all n bigger than this integer n, we have f of x naught minus fn of x naught is less than epsilon naught over 4. Okay. So if you have any questions, please let me know. Or if you want me to go back, and we have that. But Gn of epsilon is continuous. It's continuous. So there exists a delta epsilon such that so it's continuous, and namely it's uniformly continuous because 0, 1 is compact. So this is the Hein-Cantor theorem. Well, yeah, we're not really using that. Okay, so there exists a delta epsilon global. So it's a global guy. such that if you have x minus x naught less than delta epsilon, then you have gn of epsilon x, gn of epsilon x naught, is less than epsilon naught over 4. Okay, so now let's put these two together to get the claim. So, yeah, and then one more thing, and we have monotonicity. So we have if n is bigger than an epsilon, we know that gn of x is less than gn of epsilon x by monotonicity of fn. Yeah, okay. Can you explain the graph you showed above? Yes, definitely. So let's see what's going on. So are you happy with this? Meaning, you know, since x and k goes to x naught, it eventually falls inside the ball. Oh, the GNX. Okay. Yeah, sure. So, I mean, yeah, let's look at the claim. So where's the claim? I will draw it again close to the claim. Yeah, here. So let me draw it here. Here. Okay. So it says that there is a neighborhood. What's going on? Yeah. So like this. So there is a neighborhood. So you have this upper bound, the epsilon over 2, and it says that if x falls inside this ball, so x is here, then gn of x is below that. So this gn of x. Is that okay, Tongfei? So we're proving this claim now. So we're proving that this is true. And I drew a picture of it. Okay. For pointwise convergence, we work with absolute values rather than sup norm. That's right. Yes. So where's my? Yeah. So this is the pointwise. So here, what we mean by pointwise, we mean absolute value for fixed x. Let me call it x naught and x naught. So you fix x naught. As you take the limit, it goes to 0. But here you don't fix it. Here you don't fix x naught. Here you look at over all of them. And this guy goes to 0. Yeah. Okay. Yeah, thank you guys. Yeah, feel free to keep asking. All right, so yeah, let me remind you where we were. By the way, I gave you the OneNote link, so you can also move through it yourself. You can find it in the announcements. I gave you the link. Okay, all right, so what's going on? Yeah, so we have this is less than epsilon, this is less than epsilon. Yeah, and we wanted to prove the claim. So yeah, we put this so all together. We get 0 less than for all n bigger than n epsilon. It's like this. This is less than g and epsilon of x. We do, how do you call it? We do triangle. So like that. We do triangle. And then this guy is controlled by continuity. And this guy is controlled by pointwise convergence. So indeed, we get the claim. Okay, that's it. That's pretty neat. So it tells you, let me reiterate. If you have continuous functions increasing, and you have some pointwise limit, then on a compact set, but it's actually true more generally. We just don't have the technology here yet. Then you can swap. So I made no mention of uniform, right? So just by monotonicity and pointwise and monotonicity, you get your the things swapping. So no need to prove uniform. We did it for you, so you can. So you can just reference this theorem. So you can just reference. Dean's theorem. Okay. How do we get the epsilon? The first. Okay, let's see. So yeah, so this is just pointwise convergence. Here, x naught is fixed. And that's the definition of pointwise convergence. Is that okay, Bing Yao? It's just the definition of pointwise convergence. Yeah, okay, good. All right, good. So yeah, you can just reference this theorem when we have monotonicity. You don't have to reprove uniform. Good. Now let's go into Leibniz rule in the remaining time. This is also called, Feynman used it a lot, it's called differentiate under the integral. All right, so where are we? Here. Make sure I have the right statement. All right, so suppose f of xt and its partial derivative in x on 0, 1. Yeah, we'll do everything on 0, 1, but it doesn't matter really. Are both continuous. So the function is called the continuously differentiable, C1. Are both continuous, then f of then yeah, let me write it here. Then f of x equal to the integral where you integrate only in the t variable, only in t, is differentiable it's x differentiable. And you have the formula partial x of f is equal to, so you bring in the derivative. Where did you use the fact that f is pointwise convergent? I mean, we just talked about this. Like Bing Yao asked me and I just said it. Like, I don't know. What, I mean, we said right here, definition of pointwise convergence. Ying Suan? Yeah, we just said it right here. No, we used it right here. Ying Suan? Is that okay? Yeah. Okay, good. Yeah. Well, I mean, what was his name? He just asked it. Bin Yao. Yeah, so that's how we use it. The first refers to the continuity of G. I don't know what you guys mean, but yeah, to get this second guy, we used continuity of G. Yeah. We didn't use any pointwise here. Here we use continuity. On the previous part, we used. All right. So yeah, we swap limit and we swap integral and limit. And derivative. But the derivative is just a limit operation. So you'll see that we already have all the tools in hand. All right. So this is the proof is in the book, and I will try to add a few more details here. All right. So let me make sure I have everything right. The proof in the book is a bit reverse. So let me motivate what he's doing. So let me start. So by definition of derivative. So what is the definition of derivative at at the fixed point x naught is the limit as h goes to 0 of fx naught plus h minus f of x naught, right? That's the definition. And then what does he do? He says, okay, fine. Want to show. So does he have a notation for this? So so he has this guy, and he wants to show that this is equal to the how do you say it? The derivative for f. Dx of f x naught t dt. He wants to show that this goes to 0 as h goes to 0. Right? So that's what he's doing. He's proving a star. Okay. So that's the logic. All right. Okay. All right. So step one, let's rewrite this in terms of this. So f of x naught plus h, f of x naught over h. You can write this as 0, 1, f of x naught plus h, f of x naught. Yeah, there's also t. Okay, so we used the definition of f here, nothing else. All right. The second beautiful step is that partial x of f is continuous. So we can apply MVT. No, sorry. F is differentiable. So we can apply MVT. Let's see. So we're applying MVT here. You have f of x naught plus ht. By mean value theorem, there is some, I'll use the same notation. There is some xt t times the difference of the interval. For some xt in x naught and x naught plus h. Why can we have the integral with respect to t? Why can we have the integral? I don't quite understand your question. So f has two variables. For example, f of xt might equal x plus t. So you can integrate on each variable separately. Let me do it in times. So this is x times integral of t. Yeah, I don't understand. What do you mean by bottom one? I have numbers. So do you mean star? Do you mean which kind? Where? Like what is inside the integral one? Okay, yep. Oh no, this one you can do it yourself. It's not hard. So try to do this. Try to show how to get from here to here. That's not hard. Just use the definition of f. This is capital F, right? Not little f. Yeah, good. All right. So why are we applying mean value theorem? Because again, right, we're trying to control. We're trying to relate this to the derivative. Okay. Okay. So step 3. By continuity of the derivative, let me see. So yeah. So by continuity of this, for epsilon tilde, if you like, equal to epsilon over 1. Fine. Yeah, I want to follow the notation from the book. for this, there exists a delta such that, how do you say it? If you have x minus xt, so this is the same xt from here, less than delta epsilon tilde, then you get that this is less than epsilon. Yeah, I don't like this epsilon tilde. Let me just call it epsilon. So fix epsilon positive, and you get this. Okay. All right. So now we have everything. Let's put them together. Why is x a function of t? Good question. Thank you. So here we apply MVT on the x variable for fixed t. So t is fixed. I might as well call it something to make it clear. Let me call it maybe t naught. I might confuse you with x naught. Yeah, I think it's fine. Let me call it t naught. So t naught, t naught, t naught, t naught, t naught. Right, so you fix t naught, and then you get this statement. Is that okay, Jose? So it's for fixed t. Yeah. All right. Now let's put them all together. Let's put everything together. Okay. Right. So we wanted to show that thing to be small. Let me write it again quickly. We want this to be want to show that this is small, and it goes to 0 as h goes to 0. Okay, fine. So using 1, this becomes 0, 1. You know, how do you call it? Yeah, let me write this step by step. So yeah, this becomes xt t. Wait, what was 1? Let me make sure. Okay, that was 2, and that was 1. Okay, let me do 1 first. So using 1, you have this. That, when we use linearity of the integral, okay, then we use step 2, you know, the mean value theorem. Oh, I have to make a small correction. So here I wrote h. I shouldn't have written this. Let me do it like this. Okay, so yeah, I can apply mean value theorem. So mean value theorem gives you xt t times h over h, like that. This is the mean value theorem. And then so we use a triangle. Like this. Okay. Right, and then we use yeah, actually, let me make a comment. So what was step 3, just to remind you? So I should add here uniform continuity, first of all, because the set is compact. So by uniform continuity, if you fix epsilon, you can find the global delta. So that if this is true, then this is true. Okay. Is that okay? Let me see. XT0 should be in open set, right? Yes, yes, yes. Thank you. Thank you very much. Yes, it's an open set. Let me fix this. Thank you. All right, so now we're here. Now we're trying to estimate this guy. Well, take H to be less than delta epsilon global. That tells you that xt minus x naught, which was less than h, is less than delta epsilon global. So by 3, we get the bound epsilon. And this is arbitrary, so you take it to 0. So let me summarize the proof. So Leibniz tells you that if you have continuous differentiable function, you can swap integral and derivative. Okay. So how did we go about this? First, we want to see what exactly do we want. The derivative has this limit definition, right? And so has this limit definition, and right. So we're trying to control this difference here. Wanted to go to 0, and we showed is less than epsilon. Okay. Now, let's see. Yeah, then we use the definition of f. So we rewrote this as an integral, and right away we see that we get the difference quotient for the f, for f. Okay, so then we're like, okay, let's try to relate this to the derivative. Let's relate it to partial f. So that's step 2. And so we apply mean value theorem. I can even remove the absolute values, not to confuse you here. So we have it like this. Right, so we did that. And that was for some x naught, for some, yeah, this is x naught. And then xt was somewhere in there. Let me put it in the middle. Somewhere over here is xt. Okay. Yeah, we're almost done. Then we want to relate. Yeah, so That was step 2. Step 3, we use uniform continuity to get global control of f when x and xt are close. And we already know this is less than h, so we just had to pick h small enough to get this statement. Okay. So yeah, back again. We use step 1. We use the mean value theorem. And then finally, we use uniform continuity. Of the derivative. Right. Okay. Anything else? We're done. So we're done for today. If you have any comments, any questions.